It is disabled. Yeah, got it. No. Right. Right. So, sorry. Hello. Well, thank you very much for the kind introduction. And extremely sorry for the delay. So I was in Manchester, but right now, as you would call in Bengali, I am Bikar. So I'm spending my time at home this month, and I plan to fly to, I'll be taking up a new position in Pennsylvania State University next month. So the work that I'll be presenting here was primarily done during my master's and PhD in ISC Bangalore in the group of Arindam Ghosh. And later on, I worked both with Arindam Ghosh and Ambarish Ghosh. So which is why I've put both the logos here to kind of uh, to let you know about my group. So primarily I worked on 2D materials. Now this field essentially started around 2000, 2004, but after the extraction of graphene, which was followed by the extraction of several other 2D materials, each having its own unique properties. For example, graphene is weakly metallic, but molybdenum disulfide, transition metal chalcogenides like MOS2, WSE2, they're semiconducting. You have boron nitride, which is an insulator with a large band gap, and you've got niobium diselenide, which is a superconductor. And the essential aim of all these new class of materials is eventually, maybe 10, 20 years down the line, to replace silicon-based electronics with much more faster as well as more miniaturized devices. So I worked on topological insulators. For example, one such representative material is bismuth telluride. So the TIs, as I would call them, form a very important part of this 2D material zoo. So now what is a topological insulator? So there are three main aspects. So as you all know that metals are primarily, they have partially filled bands. Insulators have fully filled bands, and there's a band gap. So in case of topological insulators, you have these 3D TIs, you have these metallic surface states within the bulk band gap. So the way to imagine them electronically, at least electrically, is it's like chocolate with a wrapper. So when you try to pass a current, the electrons will flow through the surface. That is in this case, if I take this example or analogy along the foil on the chocolate, but essentially the bulk will not pass any current. It's supposed to be perfectly insulating, although technically that is not the case in reality. The other key property, which is a consequence of topology and spin orbit coupling in these materials, is that backscattering is prohibited. So when an electron is going from one point to another, it can scatter through all other angles, but 180-degree backscattering without changing its spin direction by 180 degrees is not possible. And these materials show weak anti-localization, which is instead of weak localization, which is basically the tendency to localize in a sample along a disorder maybe, and a kind of a precursor to the strong localization or Anderson localization. And because of this, the samples are supposed to be highly metallic and should show large mobilities, and are useful in a lot of new applications that are coming up in the context of quantum technologies. So, and as such, there have been a large number of work which has happened in these materials since late 2005 after the invention of graphene again. So for example, one of the key uses of these materials has been in fault-tolerant quantum computation using Majorana fermions, harnessing Majorana fermions by interfacing them with superconductors and magnetic fields. And of course, these materials are already known as good thermoelectric materials, but nowadays, because they have high mobility and the surface states not supposed to are topologically protected, the dissipation in these materials is supposed to be less, and they should be useful as electrical interconnects in a variety of cases. And many groups now are working, are using these materials for spintronic applications, and of course in future, as we are seeing now, in quantum computation, which is also another key aspect of research in TCG here in Kolkata. So the field essentially started around 2005, 2009, in the context of 3D topological insulators, when in a seminal paper, Schaus and Zine's paper in Nature Physics, they proposed the presence of these linear bands in certain materials like bismuth selenide, bismuth telluride within the bulk band gap. Okay, this was followed by, which is followed by an experimental verification using angle dissolved photoemission spectroscopy. Yeah, this is from Zahid Hassan's group, in which is verified in various materials like bismuth antimony or bismuth telluride and bismuth selenide. So you can directly visualize the band structure here, and you can see, in analogy to or compare with the theoretical model here, you can see that these linear bands surface states within the bulk band gap. So typically the band gap is around 0.3 eV in these materials. And this point where is called the Dirac point, or the charged infrarity point, when the number density is supposed to be zero. Overall average number density is supposed to be zero. And one of the initial challenges, at least in the early 2000s, was getting good quality materials. So the primary material of interest used to be bismuth telluride or bismuth selenide. And because of a large amount of selenium vacancies, the bulk used to be highly disordered and with full of defects. So to observe surface states or the signature of surface states, we had to cool down the samples to very low temperatures and put really large gate voltages to change the number density to the surface bands. But overall, over time, there has been a large number of work as far as material synthesis is concerned. And now, this was one of the earlier works from, I think, Yossi Ando's group in Germany. And you can see these nice Shubnikov-Bias oscillations in these materials, because eventually people found out smart ways to get really high quality samples, so high mobility samples. And one of the ways was using a solid solution. So initially, research focused on materials like bismuth selenide and antimony telluride, but these all materials have their own defects. Some is N-type, another material is P-type. So you combine these two materials, both bismuth selenide and antimony telluride, let's say, and you achieve what is called a compensated state. So N and P separately are non-zero, but N plus P is zero, to achieve more bulk conduction in these cases. So, and of course, molecular, a lot of advancements has happened in molecular beam epitaxy. For example, all the 3D TIs, what I'll be talking about is primarily like started around 2005, but the context of topological materials is quite old. And the quantum Hall effect being the first as a topologically protected or topological sample as such, if you want to put it that way. And then we have these experimentally in mercury telluride, cadmium telluride, this quantized edge transport was seen, which is an analog, which is called the quantum spin Hall effect in Lawrence Pollenkamp's group in 2000. Sorry, this is 2007, and where you can see as you change the Fermi energy, you can see 2 E square over each conductance due to two edge channels, each adding 2 E square over each. And in 2013, the quantum anomalous Hall effect was seen in these class of materials, where we have got perfect quantization at 0 gate voltage. And Nitin Samar's group here worked on showed axion insulator state, where you can, which is a manifestation of the magnetoelectric effect, where you can change the or tune the conductance by using two magnetically different TIs sandwiched between a compositionally different TIs sandwiched between a non-magnetic TI. And these were some of the recent advances which went hand in hand with kind of the advances in material growth in these samples. And of course, there are other works. A lot of people, the groups are working on these for detection of spins for their application in spintronics. And I also worked on optoelectronics, where I interface these materials with graphene to look at their infrared properties and whether they can sense infrared photons from like 900 to 720 nanometers in these fringe. So these are some of the directions that several research groups have been working on. And what I focused on during my work at ISC was noise. And why noise? So primarily, when you look at any, there are in any electronic device, there are three kinds of noise that we see typically. One is Johnson's noise, which arises simply due to finite temperature. And the other is, and because of at finite temperature, electrons are randomly moving around, and you will get a voltage fluctuations if you measure the voltage across the sample. There is short noise, which arises due to discreteness of the charge carriers. And again, the electrons being a particle in this context will go through various scattering, and you will get a fluctuation in the voltage fluctuations. What we have been interested in our lab was 1/f noise, which arises due to the random change in the carrier number or the background disorder landscape. And the first two, both Johnson's and 1/f noise, typically are independent of the frequency, but the flicker noise here itself is dependent on the time scales which is causing these fluctuations, and as such, it is dependent on the frequency here. So now why noise? So the noise itself has been used as a probe for several critical phenomena, such as in phase transitions, vortex interactions in superconductors. Recently, it was used to probe 1D channels in bilayer graphene, as well as the presence of magnetism in graphene grain boundaries, for example, very recent work from our group which came out in PRL. Now, what our interest has been in topological insulators is to understand basically the disorder dynamics in these materials, and how does disorder and defect affect the surface transport regime in these cases. We also look at the device performance, signal to noise ratio, and another thing which is very important, especially in the context of quantum technologies, is dephasing or decoherence, and how noise affects decoherence in these materials, and what are the sources of dephasing, and all is also something that we were interested in looking. And we did use noise as a tool for identifying the defect levels in topological insulators in a variety of materials. So we must also remember in this context is that many of the materials that I'm talking about here, whether it's graphene or topological insulators, they have unconventional band structure, and they are being used in and the devices also that they're being used is kind of new. So how it is important for us to know how and they will lead to a new generation of electronics where the sources of noise and decoherence can be totally different from what we're used to. And that might eventually determine their application in quantum technologies. So which is why we are interested in kind of knowing the sources of dephasing and noise in these new class of materials. So what is noise? So where does 1/f noise originate from? So suppose you have a sample and you have one defect. Now what can happen is, due to just finite temperature, this defect can move from one position to another due to the fact that it's just at some T. Okay, and if you measure the resistance as a function of time, you will see that it fluctuates between two levels. This is called a two-level system, and it has huge consequences, especially in the context of something like superconducting qubits, where the qubit coherence is kind of determined by or diminished by the presence of two-level systems at the interfaces of, let's say, aluminum oxide, aluminum channels. And So once you have something like this, the noise itself is defined. So we record the time series, and the noise magnitude is defined as the square amplitude of the Fourier transform of the time series over the time scale that we look at. Now, if you have a two-level system like this, depending on the time scale, and there is a single defect like this, now depending, it is the power spectral density SV, which is a function of frequency, is a Lorentzian. Now, depending on the time scale, you can see that it evolves and the shape changes. Now, in a real sample, of course, you have many defects. And so you have got many different time scales associated with the fluctuations. And if you look at a typical voltage, you will no longer find two-level systems, but a random fluctuation like this. And so simply due to superimposition of these time scales, you no longer get a Lorentzian, but a 1 by f behavior of the power spectral density. So this is where 1 by f noise originates in our samples, in typically in general in all samples. And in the context of devices that we make, especially FETs, field effect transistors, or in the context of silicon MOSFETs where there are inversion and accumulation layers, two other sources of noise in addition to defect motion is the random. So these substrates, in our context, we have silicon oxide, which acts as the gate dielectric. And there are these dangling bonds which can trap electrons from the channel and the substrate. So this continuous random detrapping and detrapping can give to carrier number fluctuations, which is called Mercator model, and typically goes over as 1 by n square. In addition, in our samples, if they're not encapsulated, one can have surface adsorbents, impurities, which can come during device fabrication, which can again trap electrons or P or N type, or the carriers rather. And this can lead to fluctuation in the resistance. The other important cause is mobility fluctuations, which are caused by Coulomb scattering due to these trap charges. And that is called a Hughes model, and that is primarily is dependent on goes over as 1 by n, and this is an empirical model which was used to model the noise that is observed in MOSFETs in the context of silicon MOSFETs. And in certain cases, pure number or pure mobility fluctuations often leads to we cannot explain. I'll come to this later, but there is mobility fluctuations which is caused due to number fluctuations, and that is called correlated number mobility fluctuations model. So there are certain contexts in the case of TI's thin samples where none of the pure number or mobility fluctuation model work, but we have to use the correlated model to estimate to understand the noise as well as estimate the defect density. So now we have to make devices, and this is one of the things we are good at. So what I used was the exfoliation method to fabricate devices, which was which was primarily pioneered at the University of Manchester. So you have a Scotch tape, which is a single crystal, any crystal. This is a topological insulator crystal, but you can replace it with, this is a general method. You can use a TMDC graphene crystal. You need a clean substrate, which is silicon dioxide wafer. We have the silicon acts as the gate, and we have 285 nanometers of SiO2 on top, which is the shiny part, which acts as the gate dielectric. And there are certain cleaning processes that we follow. And so the first step is we take the crystal and put it between the Scotch tape and we peel it off. Many of you know this, of course, but I'm just showing it in any case. And what happens is part of the crystal will come onto the Scotch tape, and then we press the wafer shiny part, the SiO2 surface, on the substrate. And what we end up with is something like this, where you can see some portions have kind of gotten transferred from the wafer, from the Scotch tape to the SiO2 substrate. So, and then you look at a microscope and do other processes. In certain cases, we have to do heterostructure fabrication. So we repeat this process for different kinds of materials. We exfoliate one kind of material on SiO2, then we pick it up, use a polymer or a glue to essentially pick it up below a microscope. Then we put it on top of another material which has been exfoliated on another substrate. And we pick them up and then we drop them on a pre-patterned substrate. We remove the polymer, and eventually what we do is electron beam lithography, and followed by thermal evaporation or sputtering of gold contacts. So these were some of the typical 2 or 3 or 4 layer samples that we have fabricated during our work on these materials. So our interest is primarily to look at the origin of noise in the surface transport regime. So the first question is to establish surface transport itself. So we make FETs like this. This is a scanning electron microscope, and we do 4 probe measurements. So these are your source and drain contacts, and these are your voltage contacts. And SiO2 is the dielectric. This is the channel, and we do measurements in these samples typically in a constant current circuit. So our choice of material was this quaternary alloy or a solid solution, bismuth, antimony, tellurium, selenite. So Bi 1.6, Sb 0.4, T2, Se. So essentially, this is a combination of bismuth telluride and antimony selenite. One of them is p-doped, one of them is n-doped. So you mix them so that you reach a compensated state where the bulk is supposed to be insulating. So it was seen that this material offers sufficiently insulating bulk transport. And the way we established surface transport was we looked at different thicknesses, and this is the standard process nowadays. So we looked at materials of different thicknesses. We looked at how the resistance versus temperature evolves as a function, and we see that at below 50 Kelvin, irrespective of the thickness, the sheet resistivity, surface resistivity kind of saturates in a band between 1 to 5 kilo ohm per square. So this is the way we kind of establish surface transport. And we saw from our models and fittings also that irrespective of thickness, below 50 Kelvin, it is in all the samples, it is surface transport in our case. And beyond that, the bulk starts to dominate. So now we come to noise measurement. So we essentially use a constant current circuit, and we pass, depending on the sample, we probably pass around 100, and the temperature, we pass around 100 to 10 nanoamperes of current. And we record the time series from which we calculate the power spectral density. And then, of course, we change different parameters like temperature, number density, and magnetic field. And we do these measurements typically from 20 millikelvin in a dilution refrigerator to our own lab-made variable temperature insert, where you can heat up the sample from 4 Kelvin to 300 Kelvin. And yeah, so the first thing to check is in a standard transport is to check the gate voltage dependence. So we put some backgate voltage. We see that the resistance is changing. This is because of a capacitive effect, and the number density is changing now. When we do noise measurements in these samples, we see that the noise itself, that is the power spectral density, integrated delta R square by R square is the power spectral density integrated over the entire bandwidth of measurement. And we see that noise itself increases monotonically from, let's say, from 0 voltage towards the Dirac point. And at the lowest temperature, we do observe some non-monotonicity in these samples. So we check that it is 1 by n type, and the Hoots type mobility fluctuations model kind of satisfactory. Dirac point in this case is here, negative voltage. So these are all n-doped samples. And you can see that even at 5 Kelvin, Dirac point is at like minus 60 or more. So it's extremely doped. And that is still coming due to bulk defects. The other problem is this is a 100 nanometer sample, and we did not have a, I don't want to say problem, but we did not have a top gate. So we are essentially using a silicon back gate. And because it's a 100 nanometer sample, I think we are effectively tuning only the bottom surface, which is this here, and not the top surface. So rest of it is getting screened. So that means that is also having an effect on these measurements. So that is not the case in thinner samples. So we did. We did not start at that point with top gates. Plus the problem, no, in exfoliated samples, we never got thick enough or large enough samples to put a top gate. That is another concern that we have. And the other model, McHotter model, it's not very difficult now, because when we started these measurements and all, we had still not started heterostructure fabrication. So it is no longer that difficult to control using both gates. So the other model, McHotter type carrier number fluctuation, does not satisfactorily describe the thickness, describe the noise in the systems. In the surface transport regime, we check that using a certain defect, using realistic defect density numbers, and it was not found to be the case. Also because McHotter goes over as DGDVG whole square, and shape both qualitatively as well as quantitatively they do not match. So to understand the origin of noise again in the surface transport regime, we do temperature dependence of noise. And what we see is a series of peaks at characteristic temperatures in different samples, irrespective of the sample, and at different gate voltages, that is number densities. That is again screening properties. So typically in case of semiconductors, these peaks arise either due to diffusion of impurities, but that is a very large energy process of the order of electron volts, whereas we check that it is not the case in our case. And in general, these arise due to what is called generation recombination noise. So that arises due to random charge reorganization of the background, charge reorganization via the interband transitions between the impurity bands and the bulk and the conduction band in these cases, in this case. So the best way experimentally, yeah, sure. Yes. Yes. No, no. So we first check the spectrum and we integrate it over a bandwidth where for all the data points that is 1 over f. We first see the spectrum. Not in these cases. That does, but we choose a window where the 1 over f window is consistently maintained throughout the entire temperature range. So the so typically we do measurements between, let's say, point 1 or 0.1 hertz to 10 hertz. That is where we cut off all the frequencies through digital, cut off all the signal through digital signal processing. That is typically our maximum. Not in these samples, the Dattahan model, not in these cases. So we find that it does not match. Plus the generation recombination noise offers clear experimental evidence in this case. For example, what we check is the evolution of the corner frequencies in these cases. And we find that from the temperature dependence, it is not. So it is primarily Lorentz two-state kind of a system. So no, so we are trying to ascertain from the so from the time series. See, 1 over f noise, as in right here we are looking at the time series, and what we are finding is that it is a Lorentzian in these particular at certain temperatures, and from there we are trying to extract from the temperature evolution of that peak of that Lorentzian corner frequency what is the energy scales here, because they are thermally activated. That is what we are trying to do here. So this is the corner frequency. No, sorry. So basically, we take the spectrum and multiply it with the frequency itself, and we see that. So if you have something like a Lorentzian, you'll find a peak like this, which itself again evolves over temperature, and we. Yeah, it is activated. Yeah, yeah, yeah. Yeah. So from the activated nature, we extract what is the energy scales in this case. Yeah. Okay. So So yeah, so in the context of generation recombination noise, these kinds of interbed transitions actually lead to the generation recombination noise, and we to experimentally we look at the exactly the activated nature of the corner frequencies in this case, and from the fit we extract what are the energy scales of these transitions of the energy scales, and what we see is consistently two energy scales appearing in these samples. One is 20 millielectron volts, close to 20 millielectron volts, which we cross-check with other references, is due to selenium vacancies, and another peak which is close to 100 millielectron volts, which is possibly due to bismuth selenide or tellurium andesite defects. So basically, the bismuth or selenium in the crystal structure, they go and sit in these in the tellurium in place of tellurium, but we don't have we could not really find a specific reference for this material itself in this context. So in the context of thinner samples, which is 10 to 20 nanometers, found we could not really ascertain these the exact noise um, uh, what is the origin of one-wave noise, because the samples were dominated by universal conductance fluctuations, which we realized from the non-monotonicity that we see in this in the noise magnitude, and the temperature dependence which goes over of the noise magnitude, which is goes over as 1 by T. But it is important to understand the origin of one-wave noise in the thin samples, because they are thin enough to be controlled by one gate voltage, one only the back gate, as well as thick enough to not get hybridized, and the top and bottom surfaces kind of hybridize and become a trivial insulator. So we are so what we shifted to is using molecular beam epitaxial samples. So we used a 10 nanometer thin and we sample of this material, bismuth antimony tellurium, and which had an Indian backgate, and this was grown on STO, which provides a large dielectric constant, and so we can tune the number density or the resistivity, and we can tune across the gate, across the Dirac point in these samples. But even then, I mean, absolute the gate voltage is where we observe the Dirac point is still quite high, which tells you that the bulk is still, there's a lot of bulk doping, which is of the order of 10 to the power 14 at zero gate voltage in these samples per centimeter square. So to estimate the defect density in this case, we use the charge limited scattering in case of Dirac fermions, and what we find is that the defect impurity density in these samples is of the order of 10 to the power 14 per centimeter square, and which kind of matches with the Hall measurements in Hall measurements. So again, that in the context of temperature dependence of noise, we see a peak in these samples at certain characteristic temperatures. This time in this sample, it was at 50 Kelvin, which is very similar to again what we had seen in the context of our bulk samples, exfoliated bulk samples or single crystals, and we estimate using the same principle of generation recombination noise, that using the shift of the corner frequencies that which are thermally activated in this case, is that the defect level in this case is around 83 millielectron volts above the valence band in this case. Now
I ask a question here.
Yeah.
What does this shift of the corner frequency tell you?
So it just tells us that it is activated in nature.
Is active?
It is activated. The temperature dependence tells us that it is activated, thermally activated.
You can activate the sample with temperature.
So not the sample, but the bands, the energetics, they are thermally
okay.
Arrhenius type activation.
Okay, means you can activate the performance of your instruments or like devices with the temperature.
So the energetics are dependent on the energetics go or exponentially as expected for like thermally activated, as in the impurity bands themselves here in this context are thermally activated, RNAs type.
Okay, so this then it will tell you that uh, mm, the temperature range where you can operate your
Sorry?
device.
No, there is a no, kind of. No, there is a question. Hello.
Yeah. Actually, I just wanted to know, like, from this shift in the corner frequency, what you really estimate, what is your, what it really tell you about your device you are preparing here.
It tells us that uh, uh, what does the corner frequency tell us here? It just that from the temperature evolution, it just tells us that we have got two levels here which are dominating. We have two levels here which are dominating the noise in this system. Basically, at a finite temperature, there is a, so what is happening is, you can see, think of it in this way, that there is a Fermi level here, there is an impurity band here, and there is some sort of a resonance.
Okay.
So you have got two levels which are dominating, and your sample and your signal essentially, or the resistance time series essentially is fluctuates between two states. Okay. Now when that happens, it is no longer 1 by f in nature, but rather it is a Lorentzian. So we
Okay.
look, we now what we do is we look at the, so the Lorentzian will have a corner frequency essentially, and which is evident when we multiply the pass fatal density by the frequency. So now this itself, this process itself is thermally activated.
Okay, I
Okay.
understand. I can understand.
Okay. So
Thank you.
now, yeah, so from that thermal activation, we can now estimate what are the energy scales as far as this
Yeah,
process
where
is.
you can excite this.
Yes,
Yeah.
yes, yeah.
Okay. Thank you.
Yeah, sure. So we then looked at the gate voltage dependence of noise, and in these MB grown samples, and what we see is that it's qualitatively different from our thicker exfoliated samples, and the noise increases around 10 to the power 13 per centimeter square, which is roughly around bulk number density. So we can see the effect of enhanced effect of bulk disorder. And at higher number density, at higher gate voltages, the noise saturates, which is due to the nonlinear dependence of the or STO substrate rather than anything else. So the gate has no effect. Essentially, the electric field has no effect because all the dipoles have kind of polarized in this context. So what we invoke here is we have to.
One more thing. Can you
Yeah.
go back? What is this sub you have in the when you plot this number of the hole, right? With the at the 0 voltage, you have a kind of sharp transitions, right? Instead of the continuous peak.
Sorry, could you please repeat?
Your what is that, slope has changed from negative to positive, right?
Right.
Well, what is this, the reason you are plotting in gray?
Slope has changed. So first, the two colors here, A indicate different temperatures, B is the slope of the Hall curve, because you have changed the number density, you have changed the carrier type from electron to p doping.
Okay, understand. One thing is, like, you have a gray line, like broad line.
Yeah, so that is essentially this gray line responds to essentially close to the Dirac point, basically, where you have got zero number density.
Oh, so you are saying that these are the
charge neutrality point. Yeah.
Okay.
Because it is plotted as Vg minus Vd instead of Vg. So at 0, so yes, Vg minus Vd 0 is the Dirac point, basically.
So you already know that there is a Dirac point.
Yes, and we've shifted it accordingly. We just scaled the.
Okay.
So in this context, in the context of thinner ND grown samples, pure number or carrier number fluctuations whose on record or type is no longer satisfactorily explains our results. And what we have to invoke is the correlated number mobility fluctuations model. So there is carrier number fluctuations due to bulk disorder and the surface states where there is an trapping, detrapping on the of the samples, and there is associated mobility fluctuations due to that. And using this sort of a model, we can, so one of the change, of course, this can happen possibly because compared to our samples on SIU2, the screening is completely different in this context in case of STO. So that is a possibility. What we can estimate from this model is the defect density, which is of the order of 10 to the power 14 per centimeter square, which is again same as what we obtained from our average transport measurement. So this kind of tells us that the bulk disorders in these samples are responsible for noise. So, which is very interesting because in the context of other 2D materials like graphene or transition like alphagenides, the noise originates from the due to trapping, detrapping between the channel and the substrate or at the contacts. But in our context, in the case of topological insulators, the noise itself originates from the bulk. That is, they're intrinsic factors rather than extrinsic factors which are responsible for the origin of unweighted noise in the samples. So I'll leave you with a graph where we look at the Hoots parameter, which is a figure of merit for the noise magnitude that is basically area normalized noise, and we compiled this data for different 2D materials as well as standard metals and silicon MOSFET. So we can see that while graphene itself can go down to fairly low values, our exfoliated samples actually match that kind of values here. We can actually go down to 10 to the power minus 7, which is almost as low, even lower than standard metals that we use. In comparison, the MB grown samples, the noise is, the Hoots parameter itself is quite large and of the order of 1, whereas the exfoliated samples can go to -4 levels. So I think a lot of defect engineering, a lot of material quality has to be improved in the context of MB grown samples. While it looks like the exfoliated samples at least can match some of the best materials as far as the Hoots parameter is concerned. So, alpha value is so alpha is roughly around 1 for everything, all these data. Alpha is 1 by f unless it's a Lorentzian, and where it might be 1 by f square. Alpha is taken as 1. Right. Hoots parameter. Yeah. It's an empirical. Yeah. Yeah. I don't think it's discarded, but it is still being used as a even recent papers on silicon phosphorus wires, and we are still using the parameter to look at whether they're to look at how good the environment is as far as these materials are concerned for noise. So in summary, in comparison to other 2D materials, the noise here, the source of noise here is intrinsic compared to other, and it is generation recombination noise between valence and impurity bands, which leads to noise in the bulk, and correlated number and charge density leads to the noise in the surface transport. So I'll quickly show some of our results on dephasing. I'll come to the dephasing part, and which is on our work on dephasing in topological insulators at low temperatures. So essentially, what is dephasing is the time over which an electron can stay in its exact eigenstate. Now, you have got various kinds of sources which will lead to dephasing in these materials. For example, electron Coulomb interaction between electrons, electron phonon scattering, spin, or even two-level systems. Now, these surface states are being considered for as the hardware component for several quantum technologies, and it is essential to understand what are the dephasing mechanisms in these materials in that sense. So whether it's electron-electron or electron-phonon type. So we use two kinds of methods, experimental tools to look at the dephasing. One is weak antilocalization, and the other is which is a consequence of quantum interference effect. So basically, if an electron has to go from point A to point B, then this is the probability of going to that point, quantum mechanical probability. Now, if we consider backscattering, that is A and B are same, then these two paths have to be time reverse paths, and the probability actually increases. So which is called weak localization. Now, we can break that using perpendicular magnetic field, and what we see is, depending on the material, whether it is spin orbit coupled or not coupled, the conductance can either increase or decrease. If it increases, it is weak localization. In the context of topological insulators, it decreases, which is called weak antilocalization. Now, by fitting the weak antilocalization data with the well-known HLN equation, Hikami-Larkin-Nagaoka equation, we can estimate the phase breaking length in these samples. The other method that we have used is universal conductance fluctuations, which are aperiodic reproducible fluctuations in the conductance as a function of magnetic field or Fermi energy or time, and or disorder configuration. And the magnitude of universal conductance fluctuation, which is given by delta G square, is related to the phase coherence length. So we can estimate delta G square, and from that, we can estimate the phase breaking length, which is L5. And in 2D, for the electron phonon, we have L5 goes over as 1 by T, whereas for electron interactions, L5 is 1 over T to the power half. So these are our two main tools to investigate what are the dephasing mechanisms in these samples. So essentially, extract L5 either from delta G square or from a magnetoresistance, and look at how it evolves as a function of temperature. So we looked at different kinds of devices, both thinner topological insulators as well as thicker topological insulators on SiO2 substrate, on boron nitride substrate. Some were fabricated inside a glove box to remove the effect of oxygen, and and also we investigated large area ambiguous samples from our collaborators to also investigate what is the dephasing mechanism. So essentially, experimentally, we look at MR as it evolves as a function of temperature, let's say 20 millikelvin to 5 Kelvin or more. If the red line is the fit to the HLN equation, from which we can extract B5, and L5 is related to B5. So when we plot L5, the phase breaking length obtained from MR, what we find is, irrespective of the thickness, we find the exact cutoff saturation of the phase breaking length at around below 2 Kelvin in these samples. And that happens irrespective of the thickness. So we can fit it with an equation like this, where the A1T is related to electron-electron, the last term is electron phonon, but below 2 Kelvin, the temperature independent term dominates. Now, and just to clarify, we also investigate using UCF in different samples, and we again see the same kind of behavior from UCF, as well as 1 over F noise, from where we calculated delta G square, and we see that the same behavior from 3 different kinds of experimental tools. So for different materials also. So we kind of started investigating what is the origin of the saturation. So it has been seen since the 90s, or maybe even earlier, in a variety of metal films, and in graphene, topological insulators also. So there are typically various reasons which are attributed to the saturation. For example, electron temperature is one. You're cooling down the sample, but essentially the electron temperature stays the same, then all these parameters are going to be same. But we did electron temperature calibration using Cherenkov measurements oscillations to see that our electron temperature is actually around 300 millikelvin, around close to 400 millikelvin, whereas the saturation temperature is around 2 Kelvin. We checked spin orbit coupling length. So 0 point fluctuations, but this is highly debated. And this has kind of been discarded over the last decade or so. There is spin orbit coupling. So if the spin orbit coupling length itself becomes comparable to the device dimensions, one can have saturation, but we check that the spin orbit coupling length itself is very small. In our case, much an order of magnitude smaller than the saturation length. We checked for finite sized effects, that is the device dimensions. If they become of the order of the phase breaking length, then we can have such saturation, can happen in the context of our exfoliated samples, which are few microns, which are within 1 or 2 microns in size. So to look at the finite size effect, we look at MB grown samples where the saturation, where the sample length is of the order of a millimeter, whereas the saturation length itself is around 1 micrometer, 3 orders of magnitude lower. And in this context, these were grown on STO substrate. So we do see a change in the saturation temperature, which is close to 300 millikelvin in a sample. But most importantly, we looked at the effect of local moments or isolated electrons, isolated spins in these samples. So the reason we looked at it is because it has been seen that doping gold with iron can lead to a saturation of the phase breaking time. So this happens because the total dephasing rate is given by is a combination of electron phonon, and spin flip scattering. Now, at these temperatures, the phonons freeze out, and there is no effect of phonon. So we can discard the electron phonon effect, but electron increases with temperature at low T as we reduce the temperature, and whereas the spin flip scattering rate actually decreases. So a combination of these two leads to the saturation. So we tried looking at this in the context of spin flip local moments. So one of the manifestations of the presence of local moments is the breakdown of time reversal symmetry. So we first looked at whether time reversal symmetry itself is broken or not using universal conductance fluctuations. So the magnitude of universal conductance fluctuations, delta G square, is actually related to the time reversal symmetry here. And if we break the time reversal symmetry, then we expect the TRS to go down by a factor of the delta G square to go via a factor of 2. So the way we do these measurements is we do very slow RVG sweeps, and we fit a polynomial to extract delta G square and delta R square, and from that we can extract delta G square, which is the magnitude of the conductance fluctuations. Now we can do this as a function of temperature, at different temperatures as a function of magnetic field, and what we see is beyond the phase breaking field, the normalized UCF magnitude actually reduces by a factor of 2, which tells us that even if there are local moments in our samples, the time reversal symmetry itself is preserved. So the other aspect is, of course, you have local moments, but there is no long range correlation. So then we checked. This is how the factor of 2 evolves as a function of temperature at different temperatures. I can come back to this graph later. So the other other context is the other possibility is the presence of finite moments which do not local moments which does not break dimensional symmetry. So what we did was we looked at the universal conductance fluctuations, but at a large magnetic field. So this will basically freeze all the spin flip scattering. And so, but we do not really see any qualitative change at all gate voltages as far as this is concerned. So even at zero magnetic field to Tesla, as well as at different gate voltages. So this also tells us that the surface wall coupling is kind of not responsible for the saturation we observe here. So it is important because it is important to look at the saturation also because, you know, you want large phase coherence in these samples at low temperatures. But if there is a mechanism which kind of saturates, there is no point in cooling them down, right? Because you're limited by some other dephasing mechanism which we do not understand. So uh, this is a summary of all the devices that we measured here. So we looked at the saturation of phase breaking length from electron-electron, electron phonon, uh, from three different methods, basically UCF, magnetic resistance and noise. And we find that there is a saturation, but the temperature itself is also material dependent in some form. It is not dependent on trivial factors such as temperature. Does not look to be the presence of local moments, and possibly we feel that possibly it arises due to some additional dephasing from the charged particles in the bulbs. Basically, uh, because they are compensated doped systems, we have these in doped. We have these regions in the bulb which are p-doped and which are n-doped, and they can lead to additional electromagnetic fluctuations. And at low temperatures, they can lead to enhanced dephasing. So this has been seen in another paper where they say that its saturation temperature is around 100 millikelvin, but no definitive answer yet in the context of topological insulators at least. So there are a few other papers where they comment on the effect of scattering from the backscattering from non-magnetic impurities can also lead to backscattering, which can basically act as magnetic impurities, and that can also lead to it. But we haven't really followed up on this any of these. And so I'll leave you with one last graph. So we had been looking at one of the things that we had been looking at is whether all these 2D materials and semiconductors where the noise and dephasing itself is correlated. And so we compiled a lot of data, and we kind of found that if we plot the Hooge parameter versus the phase breaking length, it turns out that in many cases, it seems to us that samples with higher Hooge parameter have a lower phase breaking length, and the samples with, of course, higher phase breaking length, they typically have a less noisy environment. The Hooge parameter is lower. So we are kind of trying to understand this. One of the things, of course, is many of these materials have a better crystalline environment, and the interface is better. Screening properties in certain cases is better. So we are kind of trying to work on this. So yeah, I'll leave it here. And these are the collaborators who have supplied many of the materials, single crystals as well as individual samples. Yeah. So yeah, thank you. In case, yeah, so I'll leave it here. In case there are questions, I will be happy to take them.
I have a question which is from the first part of your talk. You mentioned about the unconventional band structures of the
Sorry.
2D. Can you hear me? Hello?
Yeah, sure.
So you mentioned about in the first part of your talk, starting somewhere, you mentioned about the unconventional band structures of the 2D materials and topological insulators.
Yes, yes.
What does that mean? Because I don't understand. It means I'm new in this field. I'm just asking for my understanding. What does it mean?
Unconventional, as in, see, most of these materials, graphene and topological insulators, they have this linear band structures, so which are still roughly quite new in terms of investigation. I mean, earlier most of us are used to, metals and all. They're primarily parabolic, the conduction band, valence band. So here in these cases, you have got this linear spin polarized band structure. That's what I mean by linear spin polarized metallic states. That's what I mean by that unconventional here in this context.
Okay. Okay.
Yeah, you had one slide that showed the topological insulator patches, several patches on graphene.
Several patches on graphene.
Yeah, one of the cartoon.
Okay, that was in the introduction.
Not in the introduction, I think. Yeah, that one. Yeah. So, what do you mean by that? I mean, that why there's small patches of that?
Oh, okay. So this is work I had done. Basically, I made graphene FETs and I put bismuth telluride nanowires on the graphene. So essentially the role, and then I shine light. So essentially the role is that bismuth telluride, because of its band gap, will absorb the photon. And then I'm going to see a significant resistance of graphene because of that. Essentially an infrared sensor.
Acha. Okay. Okay, I have another question that you have measured this amplitude noise, right? Whatever you presented.
Delta G square.
SV.
Yes, yes.
So that's the amplitude noise.
That's the amplitude. Yes,
Yes,
yes.
but in any problem, there could be amplitude noise and phase noise.
But phase noise probably not that important in the context that we are working at. It is, I think, a bigger problem in the context of RF electronics rather than here. These are all frequency regimes, as I understand. So possibly due to we don't consider noise at all.
Okay. But of course, I mean, if you have some trapping, detrapping,
Yes.
there would be phase noise involved.
Okay. We typically do not ignore. We have typically not included the effect, at least, of phase noise here. We have primarily concentrated on the autocorrelation function to extract the noise amplitude, noise magnitude.
Okay. Is there any other question?
Saurav,
Yes.
hi. This is Tanmay. I have one question. Thanks for the nice talk.
Thank you.
So my question is regarding graphene. You said that you have used graphene for IR sensing.
Right. Yes.
Yeah. And when you exfoliated the graphene, how many layers have you checked? How many layers of graphene you have transferred?
That is yes. So this was done on single layer graphene.
Oh, this is single layer graphene. Okay.
You can check it using AFM is difficult, but or whatever less reliable. You can, the best way to check is Raman spectroscopy.
Raman. Okay. And you have gotten the FWHM for.
Look at FWHM as well as the frequency. I mean wave number where the peak is coming. I mean it is 5 minutes.
Yes. And what will happen if you go for, let's say, bilayer or few layer graphene?
See, in this context, the thing is, in this context, I can tell you that the sensitivity is going to reduce because as far as the mechanism was concerned, here, what I was observing was that as I shine light, the resistance. So, okay, can I unshare the paper one graph?
No, if you have, for example, bilayer graphene, it had its own band gap.
No, it is not also not band. So the idea here is okay. Okay, I'll show you separately the figure, but I can. The thing is, from what I understood, the effect in this case was bolometry. Okay, so I was observing a change in resistance of the graphene due to transfer of hot electrons to the graphene. Now, the temperature coefficient of resistivity, dr dt, is more in the context of similar graphene than bilayer graphene, at least. Okay.
Mhm.
So, which is why if I use if I use bilayer graphene, the sensitivity itself is going to get reduced. That's what I feel.
I see. Okay.
Because of the nature of the effect of the mechanism of response in this context.
Okay. I see. Okay. Thanks for the answer. One more thing, as you mentioned, the hot electrons for graphene. I think graphene is a quite important material for terahertz generation and sensing, isn't it?
Yeah,
Have you think about that part?
No, there are plenty of people who are trying to do terahertz. I actually was, I wanted to, so my plan was, so this was the first thing that I went to PhD, and my plan was to illustrate the frequency range. So I started 17, 20 nanometer, but then, I started other things and I never followed. There are, there were other people in the lab working on this, but not me personally. No. But yes, certainly discuss these things, but no one had.
Okay, thank you.
Is there any other question? If not, let's thank the speaker